I mean, so like so, Ting, I'm sure you need to know introduction, but this is going to be my fourth time. Got our PhD professor and was a leadership fellow. So that he was simultaneously an Einstein Fellow and a Carnegie Princeton Fellow for coming here to the stars. That's the department. They run work in a traditional visual system work in modern science theory. Using deep target follow-up, observations, leverage the exploration of large scale that. And just to drive that point home, she's been involved in the Dark Energy Survey, the DESI. She's the founder of SPY, Southern Hemisphere Spectroscopic Survey. She's also involved in the Manifest Spectroscopic Explorer. And so, Ting is going to tell us today about cell streams in near field cosmology. And so, thank you, Ting, for your research. Well,
okay, great. Thanks everyone for coming, and for also thanks the committee give me this opportunity to give this talk. I was just thinking, I think this is my fourth year here. I give a talk for my job talk like in 2019, but most of you were not here. So it's great to give an update or kind of give a brand new talk, almost brand new talk that what I have been working on, my team has been working on in the past few years. And so there's a variety of things I work on the observational side, the data mining side, and instrumentation side. And I'm also going to talk about two programs that I'm mainly focused on, like what Keith talked about last week was the Chime and Cord. I'm going to talk about S5 and DESI, two of the collaborations, but more on the observational side, and a focus on particular tracer or particular object called stellar stream. So I will walk you through what those are and why they are interesting and we should study them. Okay. I'm going to start. So we'll start with, let's see if it moves. Yeah, we'll start with the simulation of dark matter. So if you have eye that you can see dark matter, this is what we expect the dark matter distribution would be around our Milky Way. So this is about 1 megaparsec box with the brighter means higher density of dark matter, and the dark means lower density of dark matter. So this matter distribution within the Milky Way surroundings and the baryons that we see that what actually our eye can see here is the Milky Way in the center. This is what predicted by the cold dark matter model, or what we currently think that is the dark matter model for what our universe. And I said that this is called from stellar stream to near field cosmology. So I need to convince people I actually, as a cosmologist, so I need to start with matter power spectra. So this is one of the tools for cosmologists to study the matter distribution. So what you're seeing here is the power spectra at a different scale you can think about. So this is cluster scale, this is galactic halo scale, and then subgalactic scale. And we have very good measurement about power matter spectra at the larger scale through a lot of these cosmological surveys. But what I'm going to draw your interest into and then convince you that this is something important to study the nature of dark matter or differentiate different dark matter models is on the small scale end. So you can see at the galactic halo scale and a subgalactic halo scale, different dark matter model here will have different predictions for how the matter clumps in the small scale. This is what we call the small scale structure. And you can see that if the dark matter is CDM, then we expect it the matter power spectrum all the way goes to as small as possible. So here is the wave number, but you can also look at the halo mass here. So this is a 10 to the 4 solar mass, and then going to all the way to Earth mass. But if you believe the dark matter is made of either fuzzy dark matter, interacting dark matter, warm dark matter, you will see these power spectra damping at the different scales. Another way to show this, if you don't feel like you are living in the power spectra universe, then you come to this, what you see. So this is simulation I showed similar to what I showed in the previous slide, but showing the CDM-based prediction of the matter distribution in dark matter subhalo versus warm dark matter. So the idea is there is a cutoff here in the power spectra for warm dark matter. Let's see which one. This orange one is warm dark matter. And so you would expect to see much fewer dark matter clumps or dark matter subhalos in our Milky Way than what CDM predicts. So different dark matter models have different predictions. In another way to think about is if you measure the cumulative number of dark matter subhalos in our Milky Way, CDM predicts it will keep increasing, while the warm dark matter will see it flatten out. And that's as a natural prediction from the dark matter model, different dark matter models, and something hopefully we could measure. So that's what an astronomer is trying to do. So again, this is the distribution of dark matter. We cannot see them, but what we can see is the baryonic matter. So besides the center that has a Milky Way there, a lot of the dark matter halos in the suburb or in the surrounding of the Milky Way will form galaxies. And those are the satellite galaxies, or what we call dwarf galaxies, orbiting around the Milky Way. So one of these large clump, not as big as our host clump in the center, but a slightly smaller, will form some galaxy like Large Magellan Cloud, LMC. So that's one of the most famous satellite galaxy orbiting around our Milky Way. And if you get a chance to go to the Southern Hemisphere, I encourage you to get a chance to see with the naked sky that you can see actually the LMC and SMC in the Southern Hemisphere. Unfortunately, we cannot do that from the Northern Hemisphere. But if you also have a lot of other dwarf spheroidals that we can see in the Milky Way with different telescopes. So this is the progress of, I would say, the wide field optical imaging survey. So before all of those things, we only know about 10 dwarf spheroidals or 10 dwarf galaxies in our Milky Way. But thanks to longitudinal sky survey, 2.5 meter, and then later 4 meter telescope, a few of those, and the 2 to I think 8 meter telescopes, including one of those that I will mention later a little bit, the dark energy camera. I worked when I was a graduate student. And then moving towards the next generation, the Rubin LSST, which is going to come online hopefully this year, and we'll have a lot of data come out. So this progress of the optical imaging survey is helping us to find those satellite galaxies. So the top, what you're seeing is LMC, Fornax, Sculper, those very well-known dwarf galaxies or classical dwarf spheroids in our Milky Way. And then those digital sky survey was finding all those ultra-faint dwarf galaxies. Those only have 1,000 to 10,000 stars, super faint, but they are definitely reside in those dark matter halos. And we are being counting them to kind of understand whether CDM is correct. Okay, then the question is, how about going to those smaller ones? if you count here how many dark matter subhalo there is, you probably will see at least, if not hundred, if not thousands, but a few hundreds. But we don't know a few hundreds of galaxies in our Milky Way. So what happened is, this is again with the subhalo mass function that what I'm showing, but the galaxy really only triggers in dark matter subhalos with halo mass larger than 10 to the 8 solar mass. And that's where that we have a strong enough or a dense enough potential well to attract enough gas to trigger star formation. All of the subhalos, and most of those in this simulation, that if a CDM is true, that they will never have enough gas or density or potential well to attract enough gas to trigger star formation. So we'll have dwarf galaxy here, but here we'll have no galaxies. We'll have these pure dark matter dominated dark matter only dark halos. So if we wanted to test the scenario here, whether it's fuzzy dark matter or interacting dark matter or warm dark matter or WIMP, which is one of the current what we believe that the dark matter, the best candidate for dark matter, we really need to probe the smaller mass scale that below 10 to the 8 where the galaxy cannot form. So the question really is, how do we detect a complete dark subhalos? And that's something, one of the tasks for astrophysicists try to explore. And this where the stellar streams comes in. So the streams, it's like the river on the sky, but really it's, think of that Milky Way like galaxies are assembling and creating smaller systems. Those are dwarf galaxies like what I showed before. Also, some of those are globular clusters. And those things, when they get close to the center of the Milky Way, the strong tidal force from the Milky Way pulling those apart. So in this simulation, the green are the star particles, the globular cluster-like system, and the red is the dark matter particles, dark matter distribution. So you will see that the Milky Way is tearing apart all of those stellar particles and then form these ribbons-like structures. And that's how we've actually identified these linear like ribbon-like structure on the sky, what we call stellar stream. So this is the view of streams in the Northern Hemisphere when Sloan Digital Sky Survey come online. So we find these very tiny, very thin, long streams. This is a very famous GD1 stream. And there's also Power 5 stream, which is a globular cluster in the center here. It's a Power 5 globular cluster with its tidal tail. We also see these dwarf galaxy stream, which are much wider and much diffused. This is a Sagittarius stream coming from the Sagittarius dwarf galaxy. And there's another stream here is slightly thinner, but also much wider compared to the GD1 stream here. So it's called orphan stream because it's the first dwarf galaxy stream that has no progenitor identified. So that's how the name comes from. So why it is important to study these streams, as I mentioned, we wanted to study the subhalo mass function to answer the question whether dark matter is cold or warm or self-interacting. Or the other way to ask is, can we really find dark matter subhalos at 10 to the 7 solar mass or below, where we know that there will no star formation triggered. So how we can distinguish these two pictures while we cannot do this by counting the galaxies, because we know those dark matter subhalo will not form galaxies there anymore. This is where the stream we think can help this job. So what you're seeing here is just in the stream view, and then you see the gap formed here. And then later there's another one in the simulation that another one formed here. What in this simulation happened is, besides the top simulation, the simulation in the top panel, here there was 2 subhalo flyby. So they put in some dark matter only with certain structure and then let those dark matter subhalos go perturb the stream. And where the impact happened, the stars had some impulse, so they will move towards where the impact happened and then move away, and they actually oscillate. And so we will see this kind of density comes and goes over time. So we think these things we can see in the stellar stream, that they are not from the stream itself, but from the subhalos. Again, those subhalo can be any mass. Some of them could be above the star formation threshold that have a galaxy form there, or some of them will be lower than the 10 to the 8th solar mass threshold that will be complete dark. But we'll be able to study the density variation or the morphology and the structure of those stellar streams to infer what kind of things has perturbed in the past. So this is a simulation run by Peter Ma, who was a former undergrad here. I will, if there's time, I will talk about his work at the end of my talk, because it's a lot about forecasting. But you are seeing here is, I will run this again. What you're seeing here is a stream have a 10 to the 8 solar mass impact, and then you can see this make a big gap there. So that is what we see. These are the baryons that we can actually detect, we can observe, but there is a dark matter subhalo that passed by that we cannot see that. So that is to show you how we can use stream to study that. And here, if you look at the star particle distribution without perturbation, then it is the blue one. And with the perturbation, you can see there is a big gap there. Okay, so that is what we think it could happen. And in reality, how about the observations? So what I'm showing here is this stream called the GD1 I showed earlier in the Sloan Digital Sky Survey map. And on the top, what you're seeing here is a group of high probable member stars we think that belonging to GD1, we think are the members. And you see that the stream is definitely not smooth. It has something we call spur feature here, is some gap feature here. And then Bonazza et al. In 2019 tried to see if they can do some modeling by throwing in a perturber in to match with this morphological. So all what they do is they throw something in to match this morphology, the track, to mimic this thing. And what they got is some perturber happened 10 to the about half giga years ago with a mass about 10 to the 6 solar mass. So definitely much smaller than what those galaxies that we know in our Milky Way. And then the scale radii about 10 to the 10 parsec, and then with a speed about 250 kilometers per second when this perturbation impact happened. So this is very cool. This is the first kind of smoking gun saying we actually see a 10 to the 6 solar mass something, right? It doesn't have to be dark matter subhalo, but we cannot see any globular cluster in that orbit. So it's not some known globular cluster. So we think it could be something dark. But what Bonazza et al. Put in the size and mass regime. So again, it's 10 to the 8 solar, 10 to the 6 solar mass or smaller. And then it is, so it's in this area. And then it is 10 parsec. So it's very in this region. So it's very compact. And if you ask what are the lambda CDM says about the mass and size relation, should be this region. So the dark matter subhalo, if it is really, it should be much puffier, or say much bigger compared to what this best fit result. So it could be a dark matter subhalo, but it's a compact dark matter subhalo that's not land into the lambda CDM model. So that's a question. There's a spur, this feature coming from a perturber of a compact perturber. And in the same year, the other paper come out, De Broglie et al., they show that the spur can be caused by the interaction with Sagittarius dwarf galaxy with the stream a few 100 million years ago. However, it is the uncertainty for the orbit of the Sagittarius dwarf is very big. So it's only a few certain realization this could happen. So this definitely give a possibility that we can find some this dark matter subhalo. But on the other hand, I think we need more data to conclusively say this is the right picture. But this is one of the things that we use the stream to study the dark matter property. And the other part that stream is powerful is to measure the mass and potential of the Milky Way. So the question we can ask here is, what's the mass of the Milky Way? Is it 0.8 or 0.8 or 1.6 times 10 to the 12? And what is the shape of the Milky potential? Is it spherical or triaxial? So I'm zooming in this plot from the review article that you can see there are, I think, like 50 papers trying different methods to measure the Milky potential, and they disagree by a factor of 2. Although you can say, oh, if you calculate the average of those, then you can get something close to 1. Maybe that's what the Milky Way mass is. So it is important to know the Milky Way mass for 2 reasons. One is that when we wanted to compare the predicted subhalo mass function with the observed one, like say from the stream, we really need to know what the Milky Way mass is in order to do a better comparison. Second, when we do those orbit integration to predict what is the orbit of those subhalo, we need to know our Milky Way mass and Milky Way mass profile very well in order to actually recover that. So it is important to measure that. And that's something the stream can do as well. So if I say this is the progress of the progression of the wide field optical imaging survey, and I showed that this is what we are using to discover all those dwarf galaxies or satellite galaxies of our Milky Way. We are actually also using these to discover all of the streams, given that the stream is very powerful to study the nature of dark matter. So let me give you just a very simple example how these streams are discovered to start with, at least for the past 2 decades before Gaia came along. The idea is very simple. It's called something like matched filter algorithm. So what people are doing is picking up metal pool isochrone, scan them through distance in the color magnitude diagram. And then on the right, what you're seeing is just the stellar densities in each pixel. The dark means that there are more stars at that particular distance where there are more stars in this filter. And we can apply these to the entire those imaging surveys. So this is, again, the Dark Energy Survey that I worked on, and we used to discover a lot of dwarf galaxies, and later we moved to do the stellar stream. So you can see that we're scanning through in distance from about 10 kiloparsec to 50 kiloparsec. And then you will see that there are these linear overdensity structure comes and goes, and those are what we think are the stellar streams. So these are all these stellar stream how was discovered in the imaging survey era. And of course, Gaia complete changed the story, that especially for the nearby ones. So if we say that those ground-based imaging survey are very powerful to find the streams at 10 to 50 kiloparsec, then Gaia really revolutionized the streams within 10 kiloparsec because it has good astrometry measurement to get the distance and the proper motion. And so we really have this spaghetti view of the number of streams. And even people now start to use machine learning. Everyone likes to use machine learning. So people using this unsupervised machine learning, trying to find some linear structure on the sky with clumping in proper motion space, and then follow some isochrone structure. So this method, they find these two papers claim a discovery of about 90 new streams. So this is like the discovery, the speed is really going very fast, and for the number of streams. So I think I skipped into the game in 2018 when we find a lot of streams in the Milky Way from the Dark Energy Spectroscopic. So I try to make this cumulative number of streams that we know as a function of the year that was discovered. And I stopped in 2018 because I cannot keep up to counting all of them. But at least at the end of 2018/2019, we know about 70 of those. But if you look at the spectroscope follow-up to actually characterize them, to at least know if they are real or not, is very, very minimal. There's only like 5 of them, 6 of them we actually have spectroscopic data. So that's where that I decide to follow them up spectroscopically. So again, this is a view of the similar map as I showed before for the Northern Hemisphere, but now for the Southern Hemisphere from the Sloan Digital or from the Dark Energy Survey. And you can see these linear structures that we are finding about streams. So I know this time, I know where the streams are because I was part of the group that discovered those, and we can follow them up spectroscopically. So that's how I started the Southern Stellar Stream Spectroscopic Survey, which is the first part of the talk that I want to cover about the spectroscope follow-up. So I started this in 2018. At that time, I was a postdoc, I think a second-year postdoc. And I think that, oh, we should follow all the streams the Dark Energy Survey discovered, and let's do that. And it was very fortunate that time I went to a conference to meet some people in Australia, and then we decided to use the telescope in Australia to do all of those follow-up. So this started with the discovery of the stream from the Dark Energy Survey, and also happened 2018 was the year the Gaia released their data for proper motion, so we can use for target selection. And then we use this AAT, the Anglo-Australian Telescope, which have a powerful 2-degree field of view fiber positioner. So instead of observing one star at a time, it can observe 400 targets simultaneously with 400 fibers that can move anywhere within the 2-degree field of view. And then it connects to the spectrograph that we can use to measure the stellar parameters, radial velocities, instead and the metallicities, all of those informations. Instead of doing one star at a time, we can do 400 each exposure. And then for the brightest star, we go to a larger telescope, which here we use the Magellan telescope, because I think 2 years after this, I got to the Carnegie Fellow, which I started to have the Carnegie Access. So we use the Magellan telescope to follow up the brightest member stars identified in the medium resolution to do chemical abundance study, to study the chemical evolution of those stars and to understand how they evolved. And so far, we published a lot of papers, but we kind of have about, I think, 12 streams or 12 streams with all of the kinematic and chemical properties published on individual of them or ensemble of those. So far we published 17 papers, and we had a first public data release about 2 years ago, and we are preparing our second public data release to release all 5 years of data later this year. And here's the view of all of the 12 streams that we have identified members, and we have characterized them in the kind of map of Gaia. So this is each individual points is a member star belonging to those streams. Okay, so now back to this picture. I said I told you why stream is interesting, and the next is actually how we actually use S5 data to tackle those two questions. So I will give you some examples how we use the S5 data to show some of the understanding about these two particular questions. I'll start with the second one here, how we use streams to measure the mass profile and potential of the Milky Way. And here I'm going to just focus on one particular stream, which is this longest one in our 12 stream sample. This is called Orphan-Chenab stream. So it was first discovered as Orphan stream in the Northern Hemisphere, but then later discovered as a separate independent stream called Chenab stream. But later we find it's actually one stream. And there's a reason it was not connected at the beginning, you will see later. But this stream covers about 200 kiloparsec long on the sky with a distance range from about 10 kiloparsec from the center of the galaxy to 80 kiloparsec. So it covers a wide range that is very, very sensible for measure the mass profile. Oh, it has nothing. It's just a color means one stream. You mean these 3 points there? Yeah. So okay. So I have to say this is just we have to put pencil beams to follow up where the stream is at. We cannot do on-sky survey for S5. So we followed up these fields that where this stream is a different stream, and we happen to find those 3 points in that stream belonging to the Orphan-Chenab. Yeah. And it is still a question whether they are real members or not. I think it could be a chance of alignment too. But these are the 3 stars that follows the kinematics of this stream. That's why we color code them in red. So that means these 3 stars have the kinematic the same as this stream rather than the other one. Yeah. Okay. So now we'll show how we use the Orphan-Chenab stream to measure the mass and the potential of the Milky Way. Okay. Here, what I need to mention again is what we also recently learned in the past decade or two is LMC, which I mentioned earlier as the biggest satellite of galaxy of our Milky Way. It's coming likely to be in its first orbit, and it has a mass about 15% of our Milky Way, which is non-negligible. So if we wanted to really kind of calculate the mass of a Milky Way and the mass profile of Milky Way, we really need to understand what is the mass, what is the orbit of the LMC, and we should take that into account. And that's where actually the power of Orphan-Chenab stream comes. So what you're seeing here, the red is the observation in 6D. So you have the 3D location and then 3D motion, the vector. And what you're seeing, the blue points is a progenitor we still throw in the simulation and then let it spray the particles to mimic the stream. And what we'll see is in the last half gigayear, the LMC come into the Milky Way for the first pass. So you see the LMC comes in here. What happened is in the bottom half of the stream, the Orphan-Chenab stream got perturbed by the LMC heavily. If there's no LMC, the stream should be on the plane of this black dashed line. That's what we expect, which is what we think when we search for the member stars of Orphan when it was first discovered. It should be on this plane, and it was not on that plane. So that's why Chenab was discovered later on, nobody connect them to because they are not even on the same optical plane. But this is because, I'm going to show this again. This is because the LMC comes in and perturb, had a very close encounter about I think the minimum distance is about something like 15 to 20 kiloparsec and heavily perturbed the bottom half of the stream. And the Orphan-Chenab is therefore heavily disturbed. But that's also something useful for us that we can now use this stream not only to fit the Milky Way mass, Milky Way potential, but also fit the LMC mass, LMC potential, and also the trajectory of the LMC. And that's exactly what we did here. So what you see, this is the best fit model right now that we get. So we not only measure the Milky Way mass, but also LMC mass and LMC trajectory. Yes. Exactly. Yeah. So no. So I think the gap caused by subhalo versus these kind of what we call like deviation is essentially the same thing. It's just the dark matter perturbing things. It's all dynamic. It's just different scale. So this is a 10 to the 11, 10 to the 10, 10 to the 11 solar mass thing perturb, and that perturb is in large scale. So we see the whole stream track moves, while the dark matter subhalo perturbation that I talked about earlier, I'm talking about the 10 to the 8, 10 to the 7, 10 to the 6 solar mass perturbation, and that's making some of those gaps. So this one is not, because the stream was not that close to the, if it's a direct like hit on, I think it will make a huge gap or something. But this is really just moving like a 20 kpc away and making that kind of a huge thing. So it's not really making any of those small scale thing, but it's kind of a larger scale. I mean, larger scale in the Milky Way definition. Yeah. So that's what we see here. But eventually, these are all matter distribution affecting the perturbation. So it's the same idea, but just different scale, I would say. Okay, now we show this in a different view. So what you're seeing here is the same 60. We have a location on the sky, 5152. So you can think about RA deck, but then rotate it to be along the stream and perpendicular to the stream. The distance, and then proper motion and the velocity. So these are the three motions, and then this is the 5152 distance is three of the location. So we have the full 60. The red points is again the observation, and the cyan here is like the blue points, what you see earlier as the best fit model. So we have the data, we put in a model that we think that the Milky Way mass have certain profile, parametric, we can parameterize those, and then the LMC also has a certain parameter, and then the orbit of LMC, and we put all of those in, and then we find this best fit orbit. And this is the cyan point. And what you see here immediately when you see that, this is a paper we published already 2 years ago. The first thing immediately we see is, this is cool, it's perturbed, but we also see a prediction. There is this gigantic, what we call kink here. And it seems that this is the part where the perturbation is the strongest. So we would expect to see this kind of kink feature. So this is probably like what Chris was asking, that we see a spur in GD1. Do we see something like that? So here we see this kink feature predicted. I think that's the best thing about observer, that you make some observation, you do some calculation, now you make a prediction. And that's a challenge time. Whether we can verify, we can keep searching for member stars here, and whether we can find them and make a guess whether we did find something, or there's a different question. That's a very good question. So the distance is here, and the distance was coming from all the R Lyrae stars. So we mapped about over 100 R Lyrae stars along the stream, and it goes from something like 15 kiloparsec here all the way to like 80 kiloparsec here. I would say it is, some of the stream's progenitor is so low that they may not have enough R Lyrae. So we cannot use R Lyrae to look for low mass galaxy progenitor based streams. Yeah, but these will. That's a good question. We are working on that, but this stream we have R Lyrae. Others we can use what we call spectrophotometric distance. So we are doing that. I will actually, no, I don't have a slide here, but we are getting all of those. But I think the precision is different. Here with R Lyrae, we can get 5%. With spectrophotometric distance, we can get something like 10 to 20%. So it's a much larger error right now. Yeah. So here we have the full 60. And okay, so I think I stopped at here saying there's a prediction, there's a challenge. So whether or not we can actually get that. So we look for it, make a guess whether we are successful or not. Okay, so let me show you. So this is the, so this is where we look for. So we put a few pointings here to see whether we actually can find member stars. And that's what we got. So the red points are the member stars we identified. So it is close, but it's slightly off, but it's close. And that's the power. Like these are the parts that the photometry is not enough to find the stream. We have to do individual star because the surface brightness is so low and it's so distant. It's almost at a distance module. So this is distance module. So it's almost at something like 100 kiloparsec. So it's great that we actually found something there, and we can kind of model now better. So we need to understand, right? There is like discrepancy. So what's causing that? And what happened is the following. When we originally fit the whole model, we were using axis symmetric potential within Milky Way. is having a axis of A and B, that's a two free parameter. We are not making a triaxial potential. We just assume it's axis symmetric. The direction axis can be anywhere. So there's a degree of freedom we can put where it is in terms of the long semi-major axis as R, but we didn't allow for triaxial possibility. And here now we choose to use a triaxial halo, and now we can fit the data much better. So in order to fit the data, we need to add another parameter in. The other possibility to make this work is to change the Chandrasekhar dynamic friction parameters and to make the orbit of the LMC slightly deviate from what the normal orbit of the LMC to match the data. But this is very cool that we show that with one stream, we can constrain the Milky Way mass and the shape of Milky Way and the LMC mass and LMC trajectory all together. And now the challenge is actually try to do this for all of the stream we have. And if we can still see the same picture. We're not that there yet, but that's what we're trying to do next. Okay, now I'm going to go to my other side. I said why stream is interesting, and I wanted to show like how we use the S5 data to study this dark matter subhalo mass function. So I showed this before. This is the GD1 stream, and we see a spur and a kink feature there. And the question is, can we find more than just this one? So I'm going to go back to the discovery picture here. That I hope that I don't know which stream caught your eye first, but here is this. Actually, this is a known stream called Atlas stream, but the new stream that we discovered in this work is another stream called AAOmega stream here. So those were two streams, or considered to be two streams when the stream was discovered, because you see there is definitely some of the discontinuity there. And then we just turn this stream now from RA-DAC kind of coordinates, celestial coordinates, to phi 1, phi 2. So this is Atlas stream, this is AAOmega stream. And individual points is a member star we identify. And now we look at their velocity versus phi 1. So this is the AAOmega stream. This is Atlas stream. So basically cut around phi 1 of minus 12. And what to our biggest surprise after we follow up is these two streams, or we thought to be two streams, but actually they are seamless connected in the velocity space. They are actually one stream, and there's just with some kind of morphology discontinuity here. This is very similar to the GD1 stream, but it's 3 times farther. So GD1 is around 10 kiloparsec from us, and then the Atlas AAOmega stream is about 30 kiloparsec from us. So we see this spur and gap feature here, while here we see this spur broadening feature here. It's very similar, and we did some of the kind of qualitative estimation in order to make something like that, because it's much further away. So this gap actually is much bigger here, or the spur is much bigger here. It requires something around a 10 to the 7 solar mass subhalo to perturb, rather than like what to see that a 10 to the 6. But this is another evidence that beyond GD1, we actually see some of this kind of discontinuity in the globular cluster stream. That's very cool. Okay, so that's kind of the 2 examples I give here on just 2 different topics. I also want to highlight that we can not only study one stream at a time, but also put all of the stream together and do some population study. So I'm just going to show one example here. This is the work that we did with the first 12 stream that we have the good data, and we do some population study. These are all progenitor-free stream. That means that we don't know where they're progenitor nowadays, and their distance is between 10 and 50 kiloparsec. That's from the first 3-year data from S5. And the first thing we did is we're trying to classify them, whether the progenitor is a dwarf galaxy or globular cluster. What we use is to measure the metallicity spread. If the spread is high, we think it's originated from dwarf galaxy. If the spread is small, we think it is a globular cluster. So in our 12 stream sample, we think 50 of them are originate from a dwarf galaxy and 50% originate from a globular cluster. And then we also try to see, okay, what is the progenitor mass for those dwarf galaxy stream? Because for the galaxies, there's a mass metallicity relation. So we can infer their mean metallicity to the stellar mass. And that's what we get. So we see most of our dwarf galaxy has a stellar mass around something like 10 to the 5. So they are boundary between the classical dwarf spheroidal and ultra-faint dwarf galaxy, like what I mentioned for the intact form. And then another thing we can do is we can compare with simulations. So here, just show you one example that what we are doing. We compare the pericenter and apocenter of these dwarf galaxy stream, which are shown in the cross here, with the simulations from FIRE after consider the detectability for the pericenter apocenter. To our big surprise, there's not a good match here. Our streams are much closer with a much smaller pericenter, apocenter, compared what the fire predicts. Fires, most of those have to consider the detectability. So these things are supposed to be detectable in the current surveys, but their pericenter is around something like 40, apocenter around 150, while the stream that we currently can find in our Milky Way is much closer. So we think this is either telling us that there's some stellar feedback puffing the dwarf galaxies in fire simulation, make them more vulnerable to get disrupted, or there is a artificial stripping problem, that overstripping problem because of the resolution of fire simulation. But that's kind of a way how we can use the observation to compare with the simulation as an example. Okay, so I mostly talk about the S5 part for the stellar streams follow-up, and it shows 3 examples among the 17 paper we published. I do also want to highlight that we also do the high resolution part to study the chemical evolution, which I won't have time to talk about. You are more than welcome to talk to me about that. So streams are not only used to study dark matter, but also study the galaxy formation and the chemical evolution. We use the spare fibers to do the halo study and the low Z study. So for low redshift galaxies and for Milky Way halo study. I just want to use this opportunity to show an example that, because people were asking me, oh, S5 is great. What is the most proud or say like the best result you think from S5? And I thought about it for like a minute and said it has nothing to do with stream, which is this result. And this is also a very good example to tell people, especially the junior student. I think that's the beauty of science and being a researcher is you never know what's most exciting for you. After you work on, I spent like 5 years working on stream, but actually the most exciting result coming from S5 has nothing to do with the stream. And this is kind of the beauty of, or the joy of science. So this is a star called S5 HVS1 that has one of the spare fiber that we don't have anything to do. So we decide to look at something in the halo. And we happen to look at it, use it to look at some of the blue stars. And one of the stars, we measured a 3D velocity of 1700 kilometers per second. And so this is one of these hypervelocity stars we think that ejected from the center of the Milky Way. So the idea for hypervelocity star is that you have a binary that get close to the supermassive black hole in the galaxy center. One of them get captured and the other one get ejected. So Jack Hills predicted this should exist about 30 years ago in a Nature paper, where we don't know if there is a supermassive black hole in the center, but he thinks if there's supermassive black hole in the center, then we will see these kind of things. And people have been hunting hypervelocity star for decades. And this is what we find that S5 HVS1, we rewind the orbit. So this is the current location of it. We rewind its orbit. We think it's definitely coming from the center of the galaxy if it's ejected from the galactic plane. And also what is interesting is this is the ejection speed. It's almost the same as what we currently measure. It is higher than any of the hypervelocity star that we think that exist. So maybe telling us this is the real hypervelocity star, while the others might not be, or there's some kind of ejection mechanism making this kind of different distribution for a group of hypervelocity star at 800, and then one of those is at 1800. Okay, so that is my quick extensive review about what we have learned from S5. But if I put the picture here about the progression of the imaging survey, I want to make a counterpart for the spectroscope survey. I would say Sloan and S5 is the past. I mean, I'm still working on them, but I'm really trying to ramp them up. And what is the current is actually what I'm going to talk about a little bit next, which is what I'm focusing on, called DESI, but there's also very similar ones that are coming soon, like the Subaru telescope has PFS, Foremost, Weave, all of those spectroscopic surveys. So this is what I would consider as the current generation multiplex spectroscopic survey. So if you see that S5 is doing great things already in the past 5 years, I hope I can convince you in the next 5 minutes, DESI will be revolutionary. So DESI is Dark Energy Spectroscopic Instrument, and it's mostly for dark energy. By the way, I'm not talk about at all, but I would suggest you talk to Bibertip or Tanvir. I believe there will be a press release in 3 hours and there will be embargo lifting, telling about the evolution of dark energy. I'm not supposed to talk about all of that, but it is happening, and I know nothing about it. Sorry, but I'm mostly working on these small groups. So people think they will use all the dark time for the galaxies for dark energy, but all the bright time when it's moony, the DESI doesn't need them. So we have this Milky Way survey that are part of DESI, and I'm one of the working group chair for the Milky Way survey working group. So DESI in a nutshell, it's also a 4-meter telescope. Remember what I said earlier about the Australian telescope? It's a 4-meter telescope in the Southern Hemisphere in Australia. Here, DESI is also a 4-meter telescope, but what it did is put a 3-degree wide field in diameter. So earlier, the AT I talked about was for S5 is 2 degrees. So this one is even bigger. So it's in terms of field of view, it's a factor of 3 bigger. Instead of 400 fibers I talk about for S5, this is 5,000 fibers. So this one can observe 5,000 targets simultaneously. And you cannot use one spectrograph to look at all 5,000 objects simultaneously. So they build 10 of those. So this is how it looks like. It goes to a telescope, and then you have those 10 spectrograph here. And this is how the focal plane looks like. This is 5,000 fibers that can move within its patrol radii. So there's 5,000 of them. And each 10% of those fibers go to a particular spectrograph. And here is how the 10 spectrograph sit in a basement. And this is one of those spectrograph with 3 channels, the blue, the red, infrared. And the spectral resolution goes from about 2,500 to 5,000. And again, Milky Way survey is a really small part. It's not even the key science for it. But the idea is when the moon is up, the galaxies are too faint to observe. So they want to use them for other things. So that's why the Milky Way survey get in. We are aiming to observe things in the north and south galactic cap. So not in the plane, the Milky Way plane here. And we're trying to observe a total about 10 to 20 million of stars between 16 to 19th magnitude. And here is a little bit of the time scale for the data release. So first you see on the left is just the magnitude distribution for the data that we have in the first year. And you can see actually this today is the first year data release. That's why there is a press release happening in 3 hours. And you are more than welcome to use those data. It's all now become public for the first year. And currently we are in the 4th year of operation. So we have 3 years of data. So people within the DESI is using the 3-year data that hopefully will become public in 2027. But one thing I put down here is S5, which is the first part of my talk. We also study stars at 16 to 19th magnitude. It takes 2 hours per observation, while DESI spends 3 minutes at the same depth if it's dark, but we don't have the dark, so we use the bright time, and it's 10 minutes. So it's 2 hours, or say 120 minutes versus 10 minutes for the same size telescope, but at a better site with a better instrument and with 10 times more fibers and with 3 times bigger field of view. And so this is going to be revolutionary, I think, for what we're going to see in the next decade. And I'll go back to GD1 again. GD1 is a Northern Hemisphere target, so I cannot observe it in S5. But let's take a look at what the DESI tells us. So this is what we think the picture is. And instead of just looking at stars with pencil beams, which S5 did, we don't have to do that. So this is a plot that Emma made, a grad student here. And what you are seeing is the first year data versus the 3rd year data versus EDR. So the black points here are already published public 2 years ago. You should already have played with it if you're interested in using that EDR data. But the year 1 data, which is showed in red here, will become public tonight. So you are more than welcome to play. And internally, we currently have the 3rd year, the first 3 years data in blue. So basically, the entire sky has been covered in the area of GD1. So if say this is a picture we think in the past, this is the picture actually we are seeing now. So instead of seeing just a spur, we are actually seeing a very thin, very cold stream with a very broad, very hot cocoon structure. And Ray just had a paper to try to explain these kind of things yesterday. So you're welcome to take a look and try to see how we can use this to understand CDM versus warm dark matter. But this is kind of the picture we are seeing in the spectroscopic follow-up that we cannot do without DESI-like data. We can also go beyond the Milky Way. We are not only doing things in Milky Way, but we can go further. This is try to study the giant stellar stream, the longest stream or the most massive stream in Andromeda. And we are seeing these kind of shell-like structures in the Andromeda with just 3 hours of DESI data. And the CAC probably spent a few dozens of nights to get something similar. So this is to say the current, and it will probably take a lot of my time in the next few months. But as someone, next few years. But as someone who not only work on the science data, also active thinking about doing instrumentation, I will ask what is the next. We are working on this data, but we wanted to go further on and then see where is it. So if in the imaging side we have Sloan, DCAM, and then Rubin, and we have a good hand on the Rubin. We'll start observing in a few months. Then here is the less clear. You may heard of Mauna Kea Spectroscope Explorer. That's something Canadian is trying to push, but the European is pushing WST, the Wide Field Spectroscope Telescope. MUST is a project proposed by the Chinese university community, and then SPEC S5 is proposed by USDOE. So there's many of these high multiplex spectroscope survey proposal for the next decade. But it's really hard to say which one's going to happen or any of them going to happen. But we definitely need those. Just to convince you why we think it is important, I will just show two quick forecasting. And this is all the work related to the people that in this group. So I would like to highlight. So I mentioned Peter as an undergraduate working with me here and also Renee here, try to forecast how powerful we can constrain the dark matter subhalo. So here he used a graphic convolution neural network as encoder with the simulation-based inference to infer the posterior. And the idea is that we use all of the points here, not only in the location on the sky, but also in full 6D. And then we can constrain the mass of the subhalo. So this is the subhalo at 10 to the 6.75 solar mass. And you can see we can predict the mass to very high precision. And that's something we would like to do when we have a very good sample of streams with good measurement. And then the other example I want to show is instead of predicting a particular halo perturbation, this is try to predict the ensemble of it. So what you're seeing here is the velocity distribution for GD1 stream if it was evolved in a CDM-like subhalo versus if the CDM times 4 rate, so the subhalo is more versus it's only 30% of CDM. So the idea is if you put a stream in the Milky Way, and if there's a lot of subhalo, the stream will be perturbed much harder. But if there's very few subhalo, it will be colder. So you can measure the velocity dispersion of those streams for as ensemble and test whether CDM is correct or not. So very similar to what Ray is doing. And the idea is to do this for many streams. So this is currently led by undergraduate student Joseph Tong and Nasser, who is a first-year graduate student. The idea is go through all of the DESI streams. There's 50 of them, and we're measuring the velocity dispersion, predict what the velocity dispersion would be for CDM universe versus a WDM universe. And we'll do this not just on 1 or 2 streams, but on 50 streams. So with that, I will end my talk. I just want to know this is definitely a time that we have a lot of data coming along, starting from Sloan and then moving to DESI and then the next. And I do think while we are happy with what we are doing now, we definitely should think about the next step and building the next generation spectroscopic survey. And because we are touching this part, I just want to advertise, I believe there will be a tasty talk on building some of the multiplex spectroscopic spectrograph given by Xiao Jie on Tuesday, if you are interested in hear more about the hardware development in my group. Okay, I'll leave it here and thank you for your attention.
Thanks, Ting. We have time for a few questions.
Speaking of code, central stream use cloud. What's the explanation for that? That's that's the other question.
So this is something we did is, so these are what we believe are all member stars belonging to the stream. And then we try to fit with 2 Gaussian and narrow. These are, we think,
All the members we did is
thin stream with a broader stream with a uniform background. And here I'm showing you is only the stream members either belong to the stream, the thin stream, or the broader one, what we call cocoon. So all of those stars, and they all have the, so I only show the spatial, but we fit these not only with spatial, but also with the velocity, proper motion, metallicity. So these are all stars consistent with GD1 stream, yes. So that's what the race paper is trying to do. And the answer is a lot of subhalo. So earlier, right, the picture here is saying there's 1 perturber, but here the picture is over the 10 gig a year. the stream get perturbed by many subhalos at 10 to the 4, 10 to the 5, 10 to the 6. And this is ensemble effect. That's what we think.
The cold stream.
Still get cold stream, but some hotter. But again, I don't think one stream is enough. When we need more data of that. And I hope Anna will talk but we are doing this great detail for one stream, but we're also doing similar things for yes, in that and hopefully it's enough. Not just this function. But that's the picture. Whether one was correct, that's a picture to explain how that's actually this
Yeah.
Same thing, yeah. These are